So, how do you build hardware that can function in space? Space is one of the harshest possible environments. You're constantly exposed to radiation, wild temperature swings, and a hard vacuum. And if your design is wrong and your satellite breaks, it's not like you can send someone up there with a screwdriver to fix it. We've spent the last 2 years trying to improve on the state-of-the-art of one particular aspect of satellite design: communications between different onboard electronic systems. This is OCC for SAT, an EU research and development project. We aim to replace bulky, complicated, heavily shielded wiring harnesses and satellites with ultra-lightweight LEDs and cameras. We think this has the potential to make satellites simpler, lighter, and more cost-effective. In our previous videos, which are linked in the description, we've covered our high-level goals with the project and how we're manufacturing our test satellite assemblies. Now it's time to focus on the specifics. How do you design hardware for use in space? How specifically do you communicate with light? And how do we figure out whether this ambitious idea actually even works in practice? Like with everything else, we had to start from the basics.
Okay, so my name is Serge Dicol. I'm the CEO of Eureka. Our goal is to create, to design some embedded systems. And currently we are in charge to design the embedded system for SAT.
Serge has overseen the development of the hardware we use for OCC for SAT and spearheaded the design of the signaling protocols. His team started by validating the basics using simple, easily available hardware. Initially, we started with nanocomputers, off-the-shelf camera modules, and LEDs from the spare parts bin. With less than 100 euros of hardware, we were able to demonstrate that our core idea could work. From there, we shifted to designing development boards with hardware more representative of what would actually be used in space, things like high-quality LEDs provided by Lumileds. We also shifted over to using a custom development board which communicates with simulated satellite computer via industry-standard CAN bus, the same protocol used in cars and aircraft. Let's explore how optical communication actually works. All digital electronic devices communicate by encoding information into binary. For instance, let's say we have a temperature sensor that wants to report what it's seeing to a central computer. This message gets encoded into this sequence of ones and zeros. Here's the simplest approach we could take. We'll attach a camera module to our computer. If we then toggle an LED on and off somewhere in the camera's field of view, we can interpret the change in brightness we see from the camera as zeros and ones. If our camera is recording at 60 frames per second, we can transmit information at about 30 bits per second, minus some overhead for error correction. The problem is that this isn't terribly fast. It might be all right for something simple like a temperature sensor, but we can do much better. Let's improve things. Instead of a single white LED, we'll use 4 different colors: red, green, blue, and violet. This gives us multiple channels of information, as opposed to the one we had previously. Better, but still not perfect. Now, here's the critical breakthrough Serge's team made. The CMOS sensors in a modern camera don't capture the entire frame at once. Instead, they read in rows of pixels, one at a time. This is referred to as rolling shutter. If you've ever seen weird artifacts on videos of fast-moving objects, like propellers, this is why. So rather than reading each frame, we read each line. The camera can still run at 60 frames per second, but assuming a 4K camera, we're seeing 2,160 lines per second. Couple that with multiple color channels of information, and we have a massive increase in the data we can send. That fundamental concept is what lets OCC for SAT work. By exploiting how cameras record information, we can get vastly better data rates. Now, in practice, the details of this might be a little different. We're exploring options for this, but we'll probably want multiple emitters talking to one sensor, along with two-way communication for certain processes. For instance, we could look at where in the frame light is coming from to identify which device is transmitting, or we could assign a unique color to each device. By using simple hardware, We've been able to solve these sorts of fundamental design questions and ensure we have a solution which actually works. The final form of the OCC hardware will probably look a bit more like this, using custom space-rated circuit boards in a compact enclosure. Modules like this can transmit and receive data and connect to other satellite components via a CAN bus. So what's next? We've worked out the software and the hardware, and machined satellite simulators for testing this in context. The next phase of the project is all about rigorous testing to ensure that all of the components function together cohesively and reliably. Thanks for watching. You can follow us on social media for more information about the project. Our previous videos are linked below.